There are three main acid-base theories, which are Arrhenius, Bronsted-Lowry, and Lewis. However, we're only going to be going over the Arrhenius and Bronsted-Lowry for this class. So the evolution of acid-base theories is a classic example of scientific progress. So as chemists discover more substances that behave as an acid or a base, but they didn't fit the existing definitions, they kind of have to broaden the rules and create even more different theories or categories to place these acids and bases in. The first theory is Arrhenius theory. So you can think of this as the aqueous theory. So remember that when something is aqueous, this means that it is dissolved in water. So an Arrhenius acid is going to release H plus ions in aqueous solution. So these H plus ions are just hydrogen ions. So a hydrogen with a positive 1 charge. Sometimes we can refer to them as just protons though, because hydrogen just contains 1 proton. So when an Arrhenius acid is dissolved in water or it's aqueous, it's going to release these hydrogen ions, these positive hydrogen ions in solution. So for example, if we have HCl, which would be hydrochloric acid solution, where we have HCl dissolved in water. This is going to be an Arrhenius acid because when it is dissolved, the hydrogen and the chlorine are going to split up into their ions and they're going to ionize. So we would have some chlorine ions produced, so these negative 1 charged ions, and then we have these special H plus ions or these hydrogen ions, these protons, and that is what makes this substance an acid. Okay, so we also have something called a hydronium ion, which you'll have to know. So this is an H3O positive charge. So this is basically a water molecule that has added an extra hydrogen ion or an extra proton onto it. So hydronium ions will form as a result of this acid being dissolved in the water, and those hydrogen ions will then react with neutral water molecules to create that hydronium, the H3O+. So your Arrhenius acids are typically going to start with an H when they're written in their formula, okay? Just like that HCl. So we have this H in front. Okay, so this is going to indicate to us that this is probably a acid, and specifically an Arrhenius acid. If when this HCl is dissolved in water, it's going to split up and release these hydrogen ions in that solution. Okay, so some other things we can go over is Arrhenius acids can be placed in these more specific categories. They can be monoprotic, diprotic, or triprotic. So what these mean is protic is referring to a proton. Okay, so protic is just referring to our proton, which is our positive hydrogen ions, H+. So an Arrhenius acid that is considered monoprotic would mean that it produces a single hydrogen ion when it is dissolved in solution. So for example, that first one, HCl, there's only 1 hydrogen ion. So when this HCl is dissolved in water, it's going to split up into just 1 proton and then whatever that anion is. In this case, it's just our chlorine ion. Diprotic, di meaning 2, so that means that 2 hydrogen ions will be produced. So something like H2SO4, which is sulfuric acid, will dissolve in water and as a result will produce 2 hydrogen ions, okay, or release 2 hydrogen ions in that solution because there's 2 hydrogens in sulfuric acid. And then we can also have things that are triprotic acids, so tri meaning 3. So they're going to produce or release 3 hydrogen ions, so something like phosphoric acid has 3 hydrogens, and therefore it will release those 3 hydrogens in solution. Okay, so an Arrhenius base is a bit different. So something that is classified as an Arrhenius base is going to release OH minus ions in aqueous solution. So this OH minus ion has the specific name. They're called hydroxide ions. So really important that you remember that. So if we look at this example over here, sodium hydroxide, this solution is considered an Arrhenius base. So if we take sodium hydroxide, NaOH, and we dissolve that in water, what's going to happen is it's going to release or produce these hydroxide ions in that solution. So these OH -1 charged ions. And then in this case, because we have sodium there as well, it's also going to produce some sodium ions. But the thing that makes it a base or classifies it as a base is the fact that this hydroxide or these hydroxide ions are released in that solution. So a way that you can figure out if something is an Arrhenius base is it's typically going to end with an OH. So like your sodium hydroxide ends in this OH here. There's only one exception to this that you need to remember, and that is NH3 or ammonia. So ammonia does not have end with that OH. It doesn't have a hydroxide in it. Okay, however, it is still going to be classified as a Arrhenius base. Okay, so to just review everything again, if you aren't sure, you always have table K and table L on your reference table to check if something is classified as an acid or a base. But specifically, if something is an Arrhenius acid or an Arrhenius base, you want to remember that both of them are referring to when they are aqueous, okay, or when they're dissolved in water. Okay, so they're going to produce some sort of ion. Okay, or release some sort of ion in solution. For your Arrhenius acids, it's always going to be a hydrogen ion or a proton or a H+. And your Arrhenius base is always going to be a hydroxide ion, which is an OH-. So by looking at table K, we can also notice that for the most part, all of these acids start with hydrogen. Okay, so that indicates to us that this would be an acid. So when these are dissolved in water, when these acids are dissolved in water, they're going to be releasing those H pluses into that solution. So for example, we can just do, let's do nitrous acid. So HNO2. So let's say we took HNO2 and it was dissolved in this beaker of water. That would split up into these hydrogen ions. Okay, and then it would also produce the nitrite ions on the side. Okay, but that important part, what classifies it as an acid, is the fact that these H+ ions are there, or these protons are released in solution. Now for our Arrhenius base example, you'll notice that on table L, they will end with an OH, so they'll end with hydroxide, okay, except your ammonia, of course, okay, but we have to remember that is also an Arrhenius base as well. So if we take a different example, let's say KOH, and we dissolve that in water, what's going to happen is it's going to release those hydroxide ions in solution, those OH minuses. Okay, and it'll also, that other thing that it is connected to, the hydroxide is connected to, will also be released. So in this case, we got potassium ions. Okay, but what makes it a base is the fact that those hydroxides are released in that solution. Okay, so this is specifically for Arrhenius theory. Okay, Arrhenius, think aqueous. Okay, so these substances have to be dissolved in water. If it is an acid, it's going to be releasing hydrogen ions in solution, so H+. But if it is an Arrhenius base, it's going to be releasing these hydroxide ions, OH- ions in solution.